Hello and welcome to another video. In this video we're going to be looking at even odd tree. And in this problem you have a tree and all of its nodes are on different levels. So the root starts at level 0, then the next is level 1, level 2, level 3. And for every even level the nodes all have to be odd and increasing. And for every odd level the nodes have to be even and decreasing, left to right. So let's take a look at the examples. So in this first one, this is true, right? This is odd, has to be odd. These are even and decreasing. Then odd and increasing, and even and decreasing. So this is correct, so we want to return true. In the second example, the first level is fine, right? It's odd. Second level is even and decreasing, which is fine. But the third level is not strictly increasing. It has to be strictly increasing, and it's not, so you want to return false. And in the third example, the first level is odd. The second level is even and decreasing. And the third level is oh, actually, yeah, sorry, I missed that. So this is not even and decreasing. This needs to be even and decreasing, and the nodes are odd, right? So for every odd level, the nodes have to be even. For every even level, the nodes have to be odd. Yeah, and there's 10 to the 5th node, so you want to have like a linear time solution. So there's kind of two ways to do this, and let's talk about the two ways. I'll briefly describe one, and then I'll kind of describe the other one. So one way is to do a DFS. And the way to do this is you can basically store for every level, like what's the last node you visited, right? So in the beginning, we didn't visit anything, so we can store this in like an object or something. We start at the root, and we basically just go. We want to make sure that we visit nodes left to right, right? Or we can't actually technically visit right to left, but essentially we want to make sure like we visit the 10 before the 4, we visit the 3, then the 7, then the 9, and so on. You have to have some kind of order. You can either be left to right or right to left. And this is pretty easily accomplished by just whenever you recurse left and then right. And then for every level, we just check like, is there a node before this node? And do all the things that we have to have, are they all true, right? Like if I'm on an even level, the node has to be odd. If, all these things, and then also compare it to the node before. And so let's say we visited 10 and now we visit 4. Since we know we're on an odd level, we know this has to be, we know these have to be even and decreasing. So we just check like, okay, we're at the 4. Is it even? Yes. Is the number we visited before the 4 10? Is it even? Yes. Or not is it even, but is 4 less than 10? So let's briefly walk through that solution. I'm not going to show the code for that, but we can briefly walk through the solution. So essentially, like at level 0, and when you recurse, you just pass down like the level and the node. So at level 0, we check, okay, we're at the root. We don't really care whether we're at the root, but we basically check, is this odd? This has to be odd. It is. So if it's odd, we're going to check, have we visited anything on this level before? No, we haven't. So we're going to mark this level 0 with we only need to mark the last value we visited, so we mark 1. Then we go left. Probably need to make this bigger so I can like make it go. Okay, so we go left, and same thing, we check, is it even because we're on an odd level? Yes, it is. And have we visited anything before? No, we haven't. So at level 1, we're going to visit node 10. And when you recurse, you just pass down like the level down. So if you're at level 1, when you recurse, you just pass down level 2 and so on. So that part's pretty straightforward. So we recurse left again, same thing, we check. Let's actually move this over here so you see better. So we check, is this odd or even? So we're on an even level, so no, it has to be odd. It is odd. Have we visited anything yet? No, we haven't. So we're going to mark level 2, node 3. Then we go left one more time. Let's make this a little bigger. Right there. Same thing. It's fine to be even because we're on an odd level. Is this the first node we visited? Yes, it is. So at level 3, we visit 12. Then we recurse back up, and then we go right. Then for this node, we're going to check, is it even because we're on an odd level? Yes, it is. Have we visited anything before? Yes, we have. And remember, this has to be strictly decreasing, so 8 is strictly less than 12, so that is true. So we just replace 12 with 8 now. And this ensures that you're basically storing the least amount of information possible. You can alternatively store an array. Like for every level, you can store an array of all the elements. But because you only need consecutive elements to be strictly increasing or decreasing, it's fine to just store 1. So this will give us a little bit better space. So we recurse up here, recurse up here, recurse up here. We're done with that. Now we go down here. So we're on level 1, so it has to be even. It is. Have we visited something? Yes, we have. It's 10. And is this strictly less than 10? Yes, it is. So we can replace it with a 4. Yeah. Okay. And then we recurse right. Actually, sorry, we recurse left. So we check, is this odd? Yes, it is. Have we visited anything on level 2? Yes, we have. Is it strictly greater because this is an even level? So our node has to be greater. So it's just like a bunch of basic if statements. Like on an even level, your nodes have to be odd and greater and so on and so on. So we recurse down here then. Same kind of thing. It's fine. What did we visit before? We visited 8. 6 has to be strictly smaller, it is. And then for every node, you can just return, like, do all these things match, and do all these things match for the children. And if any child is false, then you just recurse return false for the whole thing. So that part's pretty straightforward as well. And then, yeah, so we do that. Then basically we come over here and do this kind of same thing, right? So here, on level 2, this is 9. We visited 7. 9 is strictly greater, so we'll change it to 9. Then we recurse down here. And this is the last one. And here, the last thing we visited 6. Is it strictly less? Yes. So we'll update it to 2. Then we just like recurse all the way up and return true. So that's how you do a DFS. A BFS is pretty similar, except the BFS, we can just, for every single node, we can just have a queue instead. So the way this one's going to work is pretty similar, except now we'll just have a queue. So we'll start off with the root in a queue, and then we can just keep track of the root and the node and the level. And then we just check, like, what level are we on? If we're on an even level, it has to be odd. And we check, is there a node after it? And if there's a node after it, then we'll also check those values. So let's kind of walk through this really quickly. So in the beginning, we'll have this node of value 1. And I'm going to store the node, not the value, but I'll just write down 1 here. So we're going to have node value 1, level 0, put it in a queue. Then for every single node that we pop from the queue, we will put in its children. So I'm not going to have these brackets. I'll just have it like this. And move this over so I have a little bit more space. So for this node, we're going to put in its children. So we're going to put in 10 at level 1 and 4 at level 1. So we pop it, put in its children, and then we have to make sure that it's strictly less than nodes on its level. So when we pop it, we're going to check, does the queue have anything? So when we pop this from the queue, the node, like the queue won't have anything yet because we put these in after we pop. So we pop it, put in its children. There's nothing in there yet, so this is fine. Then for this node, we're going to pop it, and then we're going to check, okay, is the node after it? There is a node after it now. Is it on the same level? Yes, it is. And because this is an odd level, the node after it has to be strictly less. So we check, is this strictly less? Yes, it is. Then we can pop it and put in its children. So we can pop it, put in its children. So we have, for 10, we just have the 3, and it's on level 2. Then for this 4-1, we're going to check, okay, is the node after on the same level? By checking the level, no, it's not. So we don't need to compare it. All we have to do is just make sure that it's even because it's on an odd level. So every time we pop a node, we'll just make sure if it's even or odd. And then we just check, is the node right after it on the same level by comparing the level? And if it is, then we have to make sure it's like strictly increasing or decreasing. And if one of those is ever false, we just return false. And if we're able to make it through our whole queue, then we'll return true. So we pop the 4, we put in its children. So we have 7 with a level of 2 and 9 with a level of 2. And notice how in a BFS, you're automatically getting like level order traversal and it's in order, right? Like we have 3, 7, then 9. So for this 3, we're going to check, obviously, is it odd or even? It's the right thing, right? We want an odd. And then we check the one after it. So this is on the same level and the one after it has to be strictly increasing. So we can just check these values. So that's fine. It matches all of our criteria. So we can get rid of all this. This node is fine. And we put in its children. So its children are 12 with a level of 3. And 8 with a level of 3. Then for the 7, we do the same thing compared to the 9. They are on the same level. 9 is strictly greater, so that's fine. Everything's fine there. And then we put in the children of 7. It's just 6 with a level of 3. Then for the 9, we compare it to the 12. They're not on the same level, so we don't have to compare, like, is it bigger or is it smaller? But it does have to be odd, which it is. And we put in its children, so 2 with level of 3. Okay. Now for 12, it's on level 3, so it has to be even. It is. We compare it to the node after it. The node after has to be strictly decreasing. It is. It has no children, so we just remove it from the queue. For 8, same thing. It's on the same level as 6, no children. 6 is strictly less, so perfectly fine. Get rid of it from the queue. Then finally for this one, same level, 2 strictly less. Get rid of it from the queue. And then for 2, there is no like node after it, so that's fine. Like we don't have to compare it to anything because there's nothing left in the queue, and it's even just like we want it. So we were able to get through our whole queue successfully. So we can just return true. So that's the BFS, and the DFS is the way I described earlier, where you just have a dictionary or something outside, and you just write down the last node you reached on every level. Either one's fine. So let's look at the BFS solution. So we have a queue. We append the root to it. Then while we have nodes in the queue, we're going to pop the node and the level. So all of our items in the queue will be the node and the level, kind of like I showed in the picture. And then we just check. So notice that for an even level, the node has to be odd. And for an odd, it has to be even. So you can do this little trick to make sure to check all these cases in one if statement. So essentially, if this basically checks, is this one odd and is this one odd? So if they're both odd or if they're both even, then this will be true. And then you want to return false, right? Because one has to be odd, one has to be even, right? For an even level, we have to have an odd node. For an odd level, we have to have an even node. So you can just do like one if statement to take care of both of those. Then we want to check for the node we popped. Is there a node after it? So if there's still a BFS and the level still matches, right? Because we only care like when we're on a node, like let's say we're on this node, and this node's after. We don't need to compare those, but if there's a node after the node we're on and it's on the same level, then we do need to compare those. So if there's a node after our current node and it's on the same level, then we have our 2 edge cases, right? Or our 2 cases. So if the level is odd, then the nodes have to be strictly increasing. So if actually, did I do that right? No, I got that backwards. Yeah, so the level is odd, then the values should be strictly decreasing, right? So these are the odd levels, this one and this one. So they have to be strictly decreasing. So if the next node is greater than or equal to our current node, then it's not strictly decreasing, we return false. And then for even, it's the other way. It has to be strictly increasing. So if it's less than or equal to it, then we return false as well. Then we basically just check for the children. So if the node has a left or right child, we just add it to the queue, and we add one more level. And we just return true if we're able to get through our whole queue successfully. So these are like the 2 main things you have to practice for trees. I think a lot of people only do DFS, so it is occasionally good to do BFS, but I think recursive DFS solutions are a lot easier, so generally I'd stick with that. But this is one that you can kind of do both ways, so I decided to do BFS because I don't do it very often. Yeah, and so we can run this one. And it's pretty good. It's like everything's kind of the same, so just run it a bunch, yeah. So we can talk about time and space. So basically, no matter what, no matter which method you choose, and for the DFS, no matter what you store, technically, like I always say, if your tree looks like this, for this, the recursive solution will be O of n space. They'll both always be O of n time because you do have to go through every node, but for this, the recursive DFS will be O of n space because you keep adding stack frames. Now, worst case scenario for BFS, because we are storing like the level, like we're going to have a level or something on there at a time. Actually, for BFS, you prefer to have this kind of thing because then you pop a node, you put in a child, you pop a node, you put in a child, you pop a node, you put in a child. So then that will only have one node, so that's good. But if your tree is perfectly balanced, then that's going to be the worst case scenario for the BFS. Because essentially you're storing like a level at a time. So if you store this bottom level, that's half the tree, so that's still O of n space. So like worst case scenario for both of those is going to be O of n space. And for the time, pretty much for almost all tree questions, you're trying to get an O of n where you visit every node only once. And that's kind of what we did here, right? We visit a node, we put in its children, we pop off the node, and so on. So this is O of n and O of n. This is like the case for 95% of tree problems, probably. So yeah. You can briefly talk about like for what kind of trees your space gets better and so on for a BFS versus DFS. So I think it is good to have like an understanding that, you know, like I said, if it's like this is bad for BFS because you store a level, but this is good for DFS, and the other way is good for BFS and so on. So yeah, that's going to be all for this one. Hopefully you liked it. If you did, please like the video and subscribe to the channel. And I will see you in the next one. Thanks for watching.